Hello to everyone. My name is Marco Rigoni. I'm a Director of Strategic Marketing for Coherent. Today is my great pleasure and honor to introduce the winner of the 2023 Couillaud Prize. This is Edoardo Vicentini. Edoardo Vicentini holds a Ph.D. from Politecnico di Milano and is currently as a collaboration with the Max Planck Institute in Garching, and also hold a postdoctoral position at the Nanogune in San Sebastian. Did I say everything right?
Yes, thank you, Marco. It's a pleasure to be here.
Okay, thank you very much. Congratulations for winning the prize. By the way, I would like to add that the prize is to honor the memory of the former and late CEO of Coherent, Bernard Couillaud, who was also a great academic. Coherent partnered with the OSA Foundation to fund the prize, which every year deliver an award of $25,500 to an early career investigator in the field of ultrafast lasers or ultrafast photonics. So Edoardo won the prize for his research in the area of tomographic imaging using a dual comb spectroscopy. So I would like to ask a few questions, Edoardo. So the first one I would like to ask you is, how did you learn about the Couillaud Prize?
So I know very well Chiara, that was Chiara Trovatello, that was last year winner of the Couillaud Prize. And since last year I saw her as a winner, I went to check on the OSA Foundation webpage, and I saw that I saw the requirement, and I thought, okay, I can also apply. I have my card to play, and luckily I'm here as a winner this year.
Comb are becoming more common in optics, and people use them for spectroscopy, for absolute frequency measurements. But I think it's the first time I heard about comb use for imaging, tomographic imaging or three-dimensional imaging. Can you tell us something more about this application, and how do you think about that?
I mean, for the people maybe that are not completely familiar with the frequency comb, let's think about the frequency comb as many continuous wave lasers that have a very fixed and controlled frequency space in between them. So we are doing imaging and three-dimensional imaging, and in particular tomography, with this laser system. And what is the difference between a standard way that, let's say all the researchers are using frequency comb? Is that we record the interference between two frequency comb, not anymore on a single detector, but on a camera. This allows us to have first of all, a two-dimensional plane of information, of interference. So we can have let's say, I call it a simple imaging, a simple imaging technique, let's say. But since we have the interference along all the pixels in all the space, we have in some way the possibility to reconstruct the wavefront of this wave that was generated. And with this information, we can also have the access to the third dimension, so the distance, let's say, by the phase of this wave. And here is where instead the frequency comb is coming as a novelty in the three-dimensional imaging, because this depth that we can measure, usually with a single frequency laser, has the ambiguity of the phase. The phase is periodic with the periodicity of the wavelength. Instead of having many wavelengths, very, very well controlled in frequency between each other, we can disambiguate this phase and reconstruct distance over a very long, let's say, very long span of distance, but still with the precision of a fraction of the wavelength of our laser.
Okay, very good. So this helps me to put in perspective. The other question I would like to ask you is that when people use combs for spectroscopy, they need a certain wavelength, maybe broad if they want to do wideband spectroscopy or focus on the application. For your specific application, do you need to use a certain frequency range, or you have a total freedom?
So I think it's good to distinguish two different cases. One is where we are just interested in the imaging itself. And so in this case, we are just interested in a wavelength where the material is, for example, if we want to see through the material that is transparent, or if we want instead to see it in reflection that can reflect it. But what we demonstrated already is that we can join the imaging, the three-dimensional imaging, with spectroscopy. So in this case, we need to cover a spectral region where we are both, I don't know, reflective or transmitting through the material, but also where there are interesting features of the material to be analyzed. So in this case, we can use our very broad spectral frequency comb, maybe also in the mid-infrared spectral region, where the fingerprint of the material are stronger. But instead, if we want just to measure the material in this dimension, we can go instead in visible or near infrared, where the laser sources are easily accessible, let's say, with more power, more control and everything. So we can work in both, and we can both work with very broad laser and also with, let's say, relatively narrow span laser. So that is not anymore, it's a constraint depending on the application that you want.
Okay, I understand that, very good. Now, if you were to bet on the first application or the first area of application for your technology, what would be your pick?
My pick is going to be some kind of a biological application, because especially in this second class of experiment that I just told you, where you merge the imaging and the spectroscopy, you can have a community of people, or also some I don't know, some industrial, let's say, industrial community that can be interesting to spend that money more to have a more complex laser system, but to have all the information together in a single experiment. So my bet is in this direction.
Okay, so in the area of biology, great, biological imaging. Now, do you see at this moment a technical bottleneck in terms of difficulty or in terms of cost to make this type of technology accessible to more and more people?
We are dealing with what is, let's say, commercially available as a laser source. So we are not developing, in this case, a particular laser source. So in this sense, we are limited from what the market can offer. And once that frequency comb and dual comb in particular are becoming, let's say, accessible for, let's say, or a broad scientific community, or even going next step to a consumer, let's say a consumer market, industrial market, then this technology that is not really adding much more technological complexity to the system can become available, let's say, for a broader audience compared to what is now.
Okay. Yeah, thank you, Edoardo. So do you see in your future potential startup, or you prefer to remain in the environment of academic research, maybe moving to new fields?
Let's say that I'm open to everything, because I really like to change what I'm working on. For example, I just shifted my center of scientific attention of research in a slightly different topics. I'm from, let's say, frequency comb, strictly frequency comb. I'm working in nano-optics, and so seeing that I like this change, I also think that maybe in the future another kind of change, completely change from kind of type of work, could be a possibility for me. And of course, starting my own startup with the colleagues and the people that I'm working with could be a very, I mean, it's a possibility. I'm not saying no at the moment.
Okay, good. And as a last question, can you give us an idea on how you're planning to spend the money of the prize?
So the money of the prize, I would like to use it to get my first level of independency, let's say, because this work is made in collaboration with the people at the Max Planck Institute of Quantum Optics in Germany. So during the year I'm going back and forth quite often, and so I want to start to get this kind of independency for the trips and that. And instead, from the, let's say, equipment point of view, what is really a limiting factor now from the setup that we have is the computing power, because starting to have broader frequency comb with higher resolution camera, the amount of data that we have to analyze is becoming really huge. We are talking about gigabyte. The first raw data are gigabyte of dimension that we need to open, frequency transform, and everything. So having a dedicated machine to do this kind of operation, it will speed up a lot this work. So.
Okay, very good. Thank you. So I would like to congratulate you again for winning the prize, and it was a great pleasure to talk to you and to learn more about your research.
It was really a pleasure to meet you, to be here at Coherent, and thank you again.
Great. So I would like to thank everybody for watching, and also I would like to remind you that if you are an early career investigator, or if you know early career investigator in the field of ultrafast photonics or lasers, the Couillaud Prize is annual. Usually the applications open in the month of December, so please consider applying for the Couillaud Prize 2024. Thank you very much for listening.